Good morning or good afternoon. We are continuing with our thermodynamic lectures. Today we want to look at heat transfer in a cooling fin. So let us say that we have heat being transferred between a liquid and a metal surface. And so in that particular case, normally most of the resistance will be in the fluid boundary with that particular wall. So what do we normally do? What is done is that you can have fins, and the whole idea about fins is that it increases the surface area. And if there's increase in surface area, there's significant efficiency in terms of heat transfer. Then, of course, the question is, when you have increased the surface area of the material, the amount of the material, have you increased the resistance also? No. The question is that even if there were resistance increase, then it is normally negligible. So heat transfer in a cooling fin. A cooling fin. So that we can have a schematic showing this fin protruding from a surface. That if we have, for example, this surface, we have a fin protruding this particular surface. Let's say we have this particular one. That's the flank of the fin. And let's have a slender one, which is much more thinner. Let's just try to draw it as best as we can. Slender one. To get it as best as we can. Let's try to get it as best as we can. So we have, that's the fin. And so, this is our fin. And like I've said, there's substantial increase in surface area, which increases the efficiency of the heat transfer. And so we can draw the heat flow lines and the isothermals. So we have that. The heat flow lines. And the isothermals. So we are drawing, these are the heat flow lines. And the isothermals. What are isothermal? Remember, those are lines representing constant temperature. And this is the case of the thick fin, where we are going to concentrate on that rectangular configuration or conformation. And this is the slender fin. It's a much slender fin. So if you have a much slender fin, then the heat flow lines are a lot simpler, and this basically reduces to a simple one-dimensional problem, so that we will concentrate on the slender fin, and so look at some element dx, which is some distance x from the surface there. So let's just make a few notes here. So the heat flow lines in the case of the slender fin, let's call it B. Let's call it K. This slender fin here, we are calling it K. This one, let's call it L, just for the sake of differentiation between those two fins. In the case of slender fins, it basically reduces the heat transfer problem into a simple one-dimensional problem. These are much more straight lines as compared to the other one where we have curvatures and so forth. So for this slender fin, what are we talking about slender? That it's thin. It's much thinner compared to this one, which is slightly thicker. So if you look at the flank of this particular fin here, it's much thinner as compared to the flank of this top fin. So just note the flank of the slender fin is thinner as compared to slender fin. Slender fin, let's just call it the one we call K, thinner than that compared to fin marked L. So that flank, that's the flank. Notice that this is thinner than that. And of course, when you're talking of these two fins, in the case of the slender fin, we are not expecting any transfers in this particular section here. Now, in general, when we are talking about heat transfer, we are always concerned about the temperature profile in that particular system. And so if we collapse back to the Fourier heat law, then in general, if we want to handle or deal with this element dx, which is a distance x from the surface, so to compute the heat transfer, we consider the element dx, which is a distance x from the root of the fin. So when I'm talking about the root, I'm talking about this particular point. So this element here, which you're talking about, dx, is the distance x from the root of the fin. Therefore, the heat transferred to this particular element, qx, the heat transferred, the element dx, when you go to the Fourier law, then that heat transferred, let's call it qx, is very simple. It will be minus k times that area, the change in temperature, that particular distance. And if we give these quantities dimensions, let us call this B1, and let us call this L1. Let us call this again L1, and that is B1, their dimensions. So in place of area then, we can put the dimensions. That's L1, we have our quantities there, so it will be minus K into L1, B1. Let's call it, instead of L1, let's just call it small l, lowercase l. Makes our life easy. Let's call it lowercase l, lowercase l. There. So it will be L, B1 dt by dx. dt by dx. Now, you already have this conformation or configuration of this fin system in your mind, so we can erase it. So you now know the dimensions are L, B1. You have seen the heat flow lines and the isothermals. You know the slender one, the one which is slightly thicker. Now, the heat transferred through that distance x plus dx transferred through x plus dx, we can represent that as q x plus dx will simply be qx transferred to the element x plus d of q q dx. So that's just element. So if you cancel these quantities in your mind, you're left with dq, which should be associated with that element dx. Just cancel it in your mind. Now, so what does that mean? So this means that if we take this quantity here and substitute it there, take that quantity there and substitute it there, then basically, what are we talking about? We can obtain dq of x, which would simply be qx minus qx plus dx. So we have qx, we have the expression for qx plus dx. So we just substitute those particular quantities and our life is simple. So we have minus kl b1 dt dx minus qx, remember qx is still the same, minus kl b1 dt dx plus, very important for us, now we are taking the derivative of qx with respect to x, so we have d of dx into minus klb 1 dt dx. So let's remove this so that we are able to use that part of the board unambiguously. Now, so if we simplify this, of course, those two, we have these two cancelling out. That's a plus sign. Remember, it's minus KLB. So minus and minus will be plus. So the two have cancelled out. So we have dqx as being equal to minus klb1 d2t squared over dx squared dx minus klb1 dt squared dx. So that if we assume that the heat transfer, the combined heat transfer of convection and radiation on this fin is relatively constant, so if we assume that the combined heat transfer coefficient for radiation and convection in the fin surface is constant, let's call it H, then it also means that then dq is minus H into 2 plus breadth dx to T minus Ts. That's the temperature at the wall, the temperature in the solution. Remember that. And so if we let T minus Ts be equal to theta, if we let T minus Ts be equal to theta, then definitely d2t squared, also d2t squared over dx squared will simply be d2 theta over dx squared. And so both must be equal. So what are we saying? So we are saying here, let's be careful as we erase so that, because there are quantities we will need to use. So we are saying that minus H 2L plus like a small l, the small l small l plus b dx into theta must definitely be equal to minus k l b1 b2 theta dx squared dx. Now, if we assume that b is much less than L, if we assume that b is much less than L, if we assume now that b is less than L, then we can simplify this expression into 2L theta dx equal to minus KL b1 b2 theta dx squared dx. And of course, you can clearly see that like terms will eliminate themselves, that dx can be eliminated that, and then of course we will have minus h 2L theta over minus k L b1 is equals to d2 theta dx squared. And of course the L's, the two dimensions will cancel out, so we are left with 2h theta over b1 is equals to d2 theta dx. So if you look at the solution of this for this particular differential equation in the handbooks, then clearly for this particular differential equation, the solutions are very simple. The solution for this differential equation, if you look in the handbook, very, very simple. Find the solution for that differential equation will be such that theta, in this particular case, will simply be m e to the mx plus n e to the minus nx. General solution for that. And so if you take, for example, the boundary values, if we take the boundary conditions and say that at the root of the fin, of course, x is 0, the root of the fin, x is equals to 0, then in that particular case, theta will be equal to m e to the 0 plus n e to the 0 minus 0. And anything raised to power 0, of course, will be 1. Remember, always note, in case you have forgotten, e raised to power 0 is 1. And so we have that theta, therefore, is m plus n. And so you can also take other boundary conditions and try to solve this particular quantities. And then theta is equal to m plus n. Where theta, remember, very important, where theta, remember, is 2h over b1 square root, and the root of 2h over b1. And so you can compute these particular expressions. So that's the direction for computing the heat transferred in a cooling fin. So we are going to pick up from there next time.